Today we're going to include our exponential and logarithm functions into integration. Now once again, integration is just the reverse of differentiation, so we're going to start with the derivatives that we took in our last chapter, and we're going to turn them into indefinite integrals here. We're going to start with exponentials. Remember that the derivative of e to the x is just e to the x. If we turn this around, this e to the x now is inside our integral, and now this e to the x is outside. Or in other words, the integral of e to the x is really just e to the x plus a constant, of course. And it's just as simple as that. There's not really too much more to say about this. The derivative of e to the x is e to the x, and the integral of e to the x is e to the x, plus that arbitrary constant, of course. Now, of course, we can also include substitution with this to do a little bit more complicated integrals, but that's about it for now. But let's go ahead and look at some problems involving this. Let's look at problem 3. The integral of negative 4 e to the x plus x squared dx. Now, this is not just e to the x, it has other stuff involved. But do note here that we don't have to do it all at once. We have multiple terms, we can do it a term at a time. For instance, the x squared here, we can do that using our power rule. We raise the power of 2 to 3, we divide by that new power. We have a 1/3. So that handles the x squared term without even looking at the e to the x part. With the negative 4e to the x, the negative 4 is a constant. So we can kind of ignore that and just integrate the e to the x and then multiply negative 4 to the result. Of course, like we just saw, the integral of e to the x is still e to the x. So we'll still have e to the x times that negative 4, and then don't forget your constant at the end. So problem 3 is pretty straightforward. Just to remember how to integrate exponentials and powers. Problem 5. This is a little bit more complicated. Here we have the integral of e to the 5x minus 3 power. Now this is not one that we can actually just split up into different terms. We do have to actually deal with the fact that the 5x minus 3 is inside of the exponential. But this is a case where we have an inside function inside of the exponential. So this is where we're going to use our substitution. It should be pretty clear here that we're going to let our u be 5x minus 3. That's really the only inside function to be dealing with. When we set u equal to that, we do need to take our differential. So our du is the derivative of this, which is 5 times dx. Now we do not have a 5 times dx in the integral already, so we're going to have to get rid of that 5 by moving it over to the other side. So we're going to have a fifth of du is equal to dx. So that dx is going to be traded out for 1/5 du. Of course, I'll go ahead and put the 1/5 outside of the integral because there's no reason to keep it inside. Here we still have the e, and it's now to 5x minus 3 is being changed to a u. And then the dx here was the 1/5 du. Now the integration is pretty easy. The integral of e to the u is just e to the u plus a constant. And our last step in doing the substitution is actually going ahead and putting it back in terms of x's. So this u here is going to turn back into a 5x minus 3. So actually, not too bad. The only thing here is that we ended up with this 1 over 5 because of the 5 multiplying the x in our exponential. We can make it a little bit more complicated, like in problem 7. Here we have the integral of 9x times e to the negative 2x squared. So we actually have a square inside of our exponential. Of course, we're going to have to do a substitution. We don't have just e to the x, so we're going to have to deal with the fact that we have something other than x in our exponential. So we'll just let u be that negative 2x squared and hope everything works out. If we differentiate this to get the differential, when we differentiate negative 2x squared, we get a negative 4x. That's going to multiply to dx. We have an x in here and a dx, but we don't have a negative 4. So I'm going to move the constant over to the other side. So that means the negative 2x squared in the exponential is going to be traded out for u. The x dx is going to be traded out for negative 1/4 times a du. In fact, I'm going to go ahead and put the negative 1/4 outside, and I'm even going to move this 9 outside as well. So we'll have a negative 9/4 outside of our integral. Inside the integral is left with an e to the u du, which we already know how to do that one. We've done that one on the last one, e to the u plus c. And of course, our last step is to trade out the u for the negative 2x squared. So just nice and simple like that. Now there is one thing about this example that kind of is interesting. Let's look at a similar situation. The integral of e, and I'll leave out the 2, but I'll have the negative x squared. Can we do this integral? If we try to make the substitution, and really the only substitution we can try here is negative x squared, and we were to take the differential here, now we can deal with the negative 2. The negative 2 comes over to the other side. But we don't have this x. This x is a big problem. Because we don't have that x, we actually can't do anything here. There's no x to deal with. In fact, this is kind of a losing substitution. It doesn't really go anywhere. And there's not really any other substitutions we can try. It turns out that this particular integral is, in a sense, not possible. Now, I'm not going to say it's completely impossible, because technically there is a function whose derivative is e to the negative x squared. But we cannot write it in terms of functions that we know how to deal with. It's actually there's actually mathematicians have come up with a special name for it. It's called the error function. That's defined to be kind of the antiderivative for e to the minus x squared. This is not a function that can be written in terms of powers or exponentials or logarithms. It can't even be written in terms of trig functions, the functions we haven't even worked with in this class. The only thing that we can actually do here is write it as an integral. So kind of just the point here is that don't expect everything to go perfectly all the time. Things will you'll definitely run into some problems in doing some integrals. But I'm not going to give you any problems like that. Don't worry about me giving you impossible problems. That's definitely not something I would do. Alright, so there's not much more to say about exponentials directly. Let's move on to logarithms. Again, we're going to start with our derivative. We have the derivative of the natural logarithm. Remember, that is just 1 over x. If we turn this around, the stuff that is outside our derivative is now going to be inside the integral. And the stuff that is inside our derivative is now going to be outside the integral. But what you might notice from here is that we didn't learn how to integrate the natural logarithm itself. We don't have the integral of the natural logarithm. But what we did obtain is something incredibly important. Remember from our power rule for integration, if we integrate x to the n, we have the formula of 1 over n plus 1, x to the n plus 1. Basically, we raise the power by 1, and then we also divide it by the new power. But we had to make the condition here that n is not negative 1, or else we're trying to divide by 0. The formula completely breaks. Well, what does that n equals a negative 1 mean? Well, x to the negative 1 power is 1 over x. Basically, we had to exclude the 1 over x case. We didn't know how to integrate 1 over x to begin with. So in essence, what we found is a patch to our power rule. In the case of n equals negative 1, instead of turning this into a power like we have here, we instead have to introduce the natural logarithm. So you can say this has multiple cases. In the case where n is not negative 1, we follow this power rule. In the case where n does equal negative 1, we instead have to use the natural logarithm. It's a special case, but it's a very important special case. Now there is one issue. The domain of 1 over x is everything except for 0, whereas the natural logarithm only has domain in the positive numbers. Can we also find the antiderivative for 1 over x in the negative numbers too? Well, it actually turns out to be a kind of an easy fix. All we need to do is get rid of the negative by introducing an absolute value sign. Instead of saying that the integral of 1 over x is just the natural logarithm, what we're going to do is say it's the natural logarithm of the absolute value of x. And that works out just fine. Note that these absolute values are going to be required for our answers to be correct. Where you're going to, so like WebAssign is going to require you to have absolute values in your answers when they are required. And I'll be expecting them on exams, or on the final, because that's the only exam left. There are a few cases where the absolute value can go away, but those are only going to be cases where we can guarantee that the inside is always positive anyways. I'll make sure to give you an example where that does happen. But in general, it's safe to just assume that you always need those absolute value signs. Now you might be wondering, can we actually take the integral of the natural logarithm? I mean, we didn't get the integral of the natural logarithm here. Is it possible to take the integral of the natural logarithm? It is possible, but it is going to require a technique that we will learn in Chapter 6. So we're not quite there yet, so just be patient. We will actually eventually find out how to actually integrate the natural logarithm. But for now, the contribution of the natural logarithm to integration is just patching this hole in our power rule. Let's go ahead and put this new rule to use. Let's look at problem 17. Here we have the integral of 1 over 3 minus 2x. Now here we do have to realize that what we have here is essentially just a first power of something on the bottom. But it's not directly. We're going to have to use a substitution here. We have a 3 minus 2x that's on the bottom. We'd like to just call that a single variable. So we're going to let u equal 3 minus 2x. We need our differential. du is negative 2 dx. Negative 2 is the derivative here. Of course, we don't have the negative 2 in here. I mean, it's down here, but we'd have to have it up on top. So we'll go ahead and divide by negative 2. That means we do have to introduce a negative 1/2. Just go ahead and put that in front. Our integral, we have a 1 over u, and then we have a du. And here's where we definitely need to have that natural logarithm. The integral of 1 over u is a natural logarithm of the absolute value of u. of course with the plus c at the end. And finally, we need to turn that u back into a 3 minus 2x. So while we started with something that looked pretty simple, I mean, it is something that has an asymptote and all that kind of stuff, but it's relatively a simple function. But its integral does require us to have a natural logarithm. There's no way of rewriting this in a way that doesn't involve a natural logarithm. That's kind of actually completely necessary in this problem, which might be a little surprising. Let's look at problem 21. Here I have the integral of x over x squared plus 1. So once again, it doesn't look like anything should involve natural logarithms at all. May not even look immediately like this is a 1 over u situation. But it is something where we do need to use some sort of substitution. There's no algebra that we can do to actually put this in another form that's going to be easier to integrate. So I'm going to just take the x squared plus 1 on the bottom, and I'm going to try to call that u. And we're in luck because when we differentiate this, our x squared plus 1 turns into 2x dx, and we in fact do have an x to go along with the dx. We don't have the 2, but constants are easy to deal with. We just pull that 2 over to the other side. So this integral here, we have to introduce the 1/2 from here, but the integrand just turns into 1 over u. And so when we integrate, we get a natural logarithm of the absolute value of u. We saw that plus c. Of course, now we need to go ahead and put in the x's, so that the u here gets replaced by an x squared plus 1. And this would be a perfectly valid answer. But I'm going to go one step further. Notice here that x squared is always a non-negative number. It's always at least 0. And when we add 1 to it, that means x squared plus 1 is always at least 1. That means that we're only dealing with positive numbers inside of this absolute value. So we can actually remove the absolute value in this particular case. And it doesn't change any of the answers. So this is a very special case. Don't expect to be able to do this all the time, but when we can do it, we might as well. At least as long as you notice that that is possible. So once again, we took a function that didn't look like it should have anything to do with natural logarithms, anything to do with logarithms at all, but when we integrate it, we definitely have to have a logarithm in the answer. In problem 27, we won't have that same problem. We're actually going to have a natural logarithm in the problem. We have the integral of 1 over x times the natural logarithm of x. What can we do here? At first glance, it might be pretty unclear where to start. It looks like that if we would try to substitution, we'd let u be the entire bottom of the fraction. But if we were to set u equal to x ln of x, when we differentiate this thing, well, we have to use the product rule here, for instance. We'd have derivative of x is 1, so we have a natural logarithm of x by itself. But then we'd have x times the natural log, the derivative of the natural logarithm of x. The derivative of natural logarithm of x is 1 over x, which when you combine that with the x that we have here, actually becomes a 1. But this derivative is not found in our integral at all. This actually isn't going to work. Nothing here actually matches up with what we have here. So we can say this failed. we could try something else instead. And this is something you might have to try out and see what happens. But there's not too many possibilities here, so eventually we'll, without taking too much time, we'll stumble upon one that works. Just let u equal the natural logarithm of x, without the x's in front. And the reason why this is going to work is that when we take the differential, when we take the derivative of the natural logarithm, we end up with a 1 over x. And so the x's here on the bottom, well, it looks like it's part of a product because we're multiplying it to the ln of x. We could also think of it as a 1 over x times the 1 over ln of x. So this 1 over x here can combine is the 1 over x that we have here. That's being multiplied to the dx. And so really, we can write this as 1 over u. The u is from the natural logarithm of x here. But the 1 over x dx is going to turn into a du. When we integrate this, of course, we get a natural logarithm of the absolute value of u. But then we also have to turn that u back into a natural logarithm of x. So we have this fun function where we have a natural logarithm inside of a natural logarithm. In fact, the natural logarithm inside of an absolute value inside of a natural logarithm. So kind of a very stacked function there. But that is what we get from this particular function, this particular integral. The integral of 1 over x times natural logarithm of x has to involve this composition of logarithms. Well, that's pretty much all that we really had to say, particularly from this section. It's really just about those two new integrals. The integral of e to the x is e to the x. The integral of 1 over x is the natural logarithm of the absolute value of x. Just remember those two rules, and we basically have everything we need from this section. And so we have a bunch of integration rules now. And while they are definitely not sufficient to integrate any function, in fact, we saw one a little bit earlier where even mathematicians don't have any way to integrate them in terms of the nice functions that we know how to work with, we can tackle quite a few functions, even more than might be obvious. The book gives us a nice collection of functions, of integrals that we can do in this section that may or may not have to have anything to do with the exponentials and logarithms. But if you look in exercises 31 through 46, there's a lot of possible integrals. These are things that you should be able to do, but it may not always be obvious what to do. And so you might have to do some algebra to change the integral and change the integrand into something we can work with, or might have to use some sort of substitution trick. I'm going to go through a few of them here, and I'm going to leave the rest of them for you to try your own hand at. Remember, practice makes perfect here, and integration is definitely something that we should practice. It is definitely something that needs practice. So I'm going to work out 3 of these, and hopefully these will give you some good ideas on how to work these problems yourselves. We're going to start with problem 35. We have the integral of e to the 2x plus 2e to the x plus 1 over e to the x. Now the obvious idea here, if you're just thinking in terms of our last section, you might try just substituting u equals e to the x. But if we were to do that, this stuff on top is not just the derivative of that e to the x. It has to just be e to the x itself. Instead, let's try doing some algebra. Essentially, I'm going to split up my fraction here into multiple fractions. We have e to the 2x over e to the x. we have 2 e to the x over e to the x, and we have 1 over e to the x. And each of these we could theoretically do separately. Now, in the first one, remember e to the 2x divided by e to the x is just e to the x. Remember, when we have a division of exponentials, we just subtract the exponent. So 2x minus x is just a single x. Here, we can actually just go ahead and flat out cancel the e to the x's. We just have a 2. This one doesn't have any nice simplifications right away, and we kind of don't want to leave it as 1 over e to the x. Might not know what to do with that one, but we can write this as instead using negative exponents. We can write this as e to the minus x. And this has now become a lot easier. We can do this term by term, and the first two terms are really easy. We know how to integrate e to the x. We know that's e to the x. 2, well, that's just 2x when we integrate. E to the minus x is a little bit trickier. Technically here we do need to do a substitution. We'd let u equal negative x. And I'm going to leave it to you to work out the full details of that. It's a relatively simple substitution to do. But it'll turn out that we get a negative e to the negative x for that integral. Of course, we always need to put the plus c at the end. But we took something that looked very complicated, some fun fraction here involving exponentials, and we turned it into something that wasn't too bad. Next, let's look at problem 42. Here I have the integral of 3 over 1 plus e to the negative 3x. Well, once again, we do have a fraction involving exponentials. Unfortunately, this time the bottom is not just an e to the x. It's a little bit more complicated than that, and that causes us a few issues. It might seem obvious to try setting u equal to the bottom. If we set u equal to 1 plus e to the negative 3x, when we take the differential here, well, the 1 goes away. We end up getting a negative 3 from doing a chain rule here. So we have negative 3 times e to the negative 3x dx. Unfortunately, this derivative is not found in our integrand at all. We don't have an e to the negative 3x. So it's kind of unclear exactly how we proceed here. Now, there actually might be a way to kind of force this to work, but it's a little tricky, and there's a much better way of doing it. So let's just consider this a failed attempt and try something else. In fact, it'll be a lot easier if we do some algebra here before we even try to do any sort of substitution. What we're going to do is we're going to multiply the top and the bottom by e to the 3x, not to the negative 3x, e to the 3x. In fact, let's just go ahead and write that out. Here we have our original integrand, and we're going to multiply the top and bottom by e to the 3x. Because what that's going to do, well, for one thing, when we multiply it on the bottom, the e to the negative 3x is just going to cancel out to be a 1. The 1, unfortunately, does become just an e to the 3x. But notice here that we now have an e to the 3x on the top. And that's going to make a substitution of the new denominator work out a lot nicer. When we differentiate this thing, sort of like how we did here, we end up with a du is equal to 3e to the 3x dx. And this time we do have the derivative. We have a 3e to the 3x on the top. We actually don't even have to deal with any constants. We have exactly the 3 that we needed. So our integral just becomes a 1 over u du. Because the bottom here was the u. The top, along with the dx, is just our du. Of course, the integral of 1 over u, we need to introduce a natural logarithm of the absolute value here. And then we get to put in 3e to the x plus 1. Now, note here, I am leaving off the absolute value signs because the exponential is always positive, and adding 1 to it just makes it even more positive. So we don't need the absolute values this time. But again, very special case. If you didn't notice that, keep those absolute value signs. You might also be kind of inclined to try to cancel the natural logarithm and the exponential, but this plus 1 actually keeps us from doing that. This is actually as good as it's going to get. We cannot write this in any nicer way. That is the best way we can do it. Let's go ahead and do one last problem. Problem 45. Here, the integral of x minus 3 over x plus 3. Now, this one looks a lot simpler than the last two. We don't have any exponentials or anything like that. We do still have a fraction. Now, you might think that the obvious substitution might be just let x plus 3 be u. And that may not work. But maybe we can make it work. Let's try it. Set u equal to x plus 3. Of course, there du is just dx because the derivative of x plus 3 is 1. The problem is the x minus 3 on top. We don't have that in our derivative at all. What can we do? Well, we've run into many situations before where we needed to move stuff around in the du equation. Mostly we just had constants that we had to divide over to the other side. But there's nothing saying that we can't do something with the u equation too. How about we take u equals x plus 3 and we solve the equation for x? If we just subtract 3 to the other side, we have that x is equal to u minus 3. We can actually use this equation here to kind of substitute out any extra x's. We can turn any extra x's into u's by replacing them with u minus 3. So this integral here, the x plus 3 on the bottom, just turns into a u. The dx here just turns into a du. The top will turn this x by itself into a u minus 3. Of course, we still have that minus 3 as well. So we've done a substitution here. We did turn this into a new integral, just involving a u. It's just maybe not as simple as you might think it would be. Now, don't always expect to be able to do something like this. Not every substitution you try can be easily solved for your x variable. But it is a trick that's handy to keep in mind. Let's go ahead and simplify this. The top is actually just u minus 6. And, well, we have another fraction, a little bit different of a fraction. At least we only have a single variable in the bottom. And this might actually remind you of something that we did just a minute ago. If you look back in problem 35, we had a complicated numerator, but just a single thing on the bottom. It was an e to the x there, but the point was, because it was only one thing and not something more complicated like it was in problem 42, we were able to split up our fraction into multiple pieces, and those multiple pieces were easier to deal with. So we're going to do that here on problem 45. We're going to split this up. We have u over u, which is just 1, minus a 6 over u. Some nice little algebra there. And this is something we can actually integrate. The integral of 1, you might think immediately that would be x, but no, we are integrating with respect to u, so we do need to change that to a u, not x. The integral of negative 6 over u is a negative 6 times a natural logarithm of the absolute value of u. We still need that plus c. Now we need to go ahead and replace our u's with x plus 3's. And we have our integral. Now there is actually one other thing we could do here. Because we end up with a plus 3 here, and that's just a constant, we can actually absorb that into the plus c at the end. We can write this as x minus 6 ln of the absolute value of x plus 3 plus c. These are technically different c's. This c here is 3 more than this c, but since we don't know what the constant is anyways, then if we're just trying to write down an antiderivative, this is good enough. If we need to know what that c is, we'd have to then go ahead and still solve for it. But it's not too important to put the plus 3 in there because, well, x minus 6 ln of the absolute value of x plus 3 is an antiderivative of the original function of x minus 3 divided by x plus 3. Alright, so that's all we're going to talk about in this section. Next week, we're going to momentarily stop talking about antiderivatives and indefinite integrals. It may seem like we're going to make a kind of a weird diversion into some unrelated stuff, but all this will fit together relatively soon. So, I'll meet you there for all that fun stuff. See you then.